robot with a distance sensor and one camera on the front, and on top of it, 4 sensor and 2 DC motor for movement. And as you can see, the map is like with 6 objects and hidden red cube. And as you can see, I will demonstrate now movement of square trajectory. Each tile is 0.5 meter, so each 1 meter is equal to 2 tiles. And for now, it's like to move in square trajectory, 2 tiles on the left, on the right, and 2 tiles on the top, and then on the left, coming back at the center. After completing center self, and it will move in H shape. The radius of the first circle is 0.5, approximately the same as 1 tile, and then go at the other circle, also at 0.5 radius. And after finishing this circle, it will initiate obstacle avoidance and search for the robot cube. Obstacle avoidance is very simple. This is a distance sensor. If one activated, it will make the robot turn at certain degree. If 2 distance sensor activated, it will turn 180 degree. In that case, it will not get stuck in case of 2 boxes of 2 objects has collided. If it's detected on the right and on the left, it will turn 180 and go back. And that will not make it get stuck or get in a situation where it will lock itself in place. So after it's avoiding the obstacles, it's heading now to the red cube here. And after detect, it will come closer to it and it will stop. And after that, placement. And here we go. Yep. And it's already detected the red bulb and stopped. And for certain elapsed time, it will detect the weight and it will head to the center. Has been programmed to be on the coordinate 0, 0 using Cartesian and the correct position and the initial condition, and using the compass to know its location, and using the GPS to coordinate its location. So thank you for watching. And for the code part for the Weebot simulation software, I have 5 controllers connected with 4 headers. The main controller is M1, and I have a position controller with a header of position controller, and Cartesian to calculate each function, calculate the Cartesian coordinate for the compass and for the GPS coordinate and its header. I will attach it at the end as appendix in the video. I will explain a little bit on the controllers and the headers and its own functions. As you see, it's like all the functions here for motor stop, motor move forward, rotate to and left, and each of these functions, for example, motor square, it will make the robot go for square for elapsed time, and I program it as a function to get easier with this function and use it in other part. And even for the obstacle avoidance for robot control here, I have 8 sensors initiated and use the function to calculate also the degree of which the robot will go into and stop and move accordingly. Even the duration it takes as shown. I'll attach this and the headers at the end of the video so you have a better.
This part of multi-sim for designing force sensor here represents as a variable resistance 1.3 kilo ohm in Wheatstone bridge configuration connected to instrumentation amplifier designed as 2 non-inverting amplifier and differential amplifier. And to demonstrate the instrumentation amplifier here, it has 2 gains, one for non-inverting amplifier and the other one for differential amplifier. R1, R3 is differential amplifier, and 1 plus R2 and R1 is for the 2 non-inverting amplifier. And other ones like connected to inverting amplifier will demonstrate Tekrat. So here I'll start the simulation for multi-sim. As you can see, the Wheatstone bridge configuration will give the maximum at 500 millivolt, and the association amplifier at 5 volt. And I will decrease the resistance for 85, it will give 310. And in case, and for Tinkrad, as you see, now implementation for non-inverting amplifier and the differential amplifier. And this code here represents the force value, getting the force pin as an input for A0. Force value more than 0.1, it will flag 1 and it will detect the object. In that case, the Weebot code will go to the current destination. As to demonstrate the code here, so for 10 Newton, it will give the voltage value of 4.95, which is approximately 5 volt. And for the value of 5.50 Newton, it will give the voltage about 0. So as demonstrated here, this is the circuit for force sensor, get the value for the force sensor and get the full range for the 5.58 Newton to 10 Newton. This is the part of Tinkrad for the robot, and as you can see, it's powered by 2 battery 9 volt and 2 DC motors for actuation using L293T H bridge and Arduino Uni with the 3 ultrasonic sensors to measure the distance. I will mention the force sensor in the next part. I've separated the Tinkrad to multiple parts, so I don't have any crash or slow simulation for the force sensor and also for the DC motors, and all work simultaneously. And as you can see in our simulation, I'll explain about the code and how it's similar to the Weebot, and I'll show code for the Weebot as well. I have defined all the constants here for the ultrasonic, and also defined the pins for output for each motor and also for ultrasonic. I have defined function for drive motor as the Weebot in drive forward and drive left, back, and brake for each motor actuation. It's like rotate left, and rotate right, and also function to drive in square and force to drive in circle and reverse circle. I will show you now the function we bought for driving the motors. As you can see now, here the motor controller for the Weebot, motor stop and motor move forward and rotate left and rotate right, and rotate left for the circle and rotate right for the circle for different kind of speed. Here for driving for circle, for example, it's different function where I need to know the linear velocity for each wheel, inner and outer, and then decide how much speed each wheel should turn. And based on that, I can make a 0.5 meter radius circle for first circle and also for the reverse circle here. For this one, I only changed the max speed for Weebot for each wheel and have the circles. And for motor square here, already mentioned the loop, how to make the drives to drive in square. Also the same here. You can see to drive in square for each angle. There's 4 angles for the square, and it has turn duration. You can call it turn duration angle. If you observe the speed for the motor during simulation, you will see it was doing the square drive for each case. And I'll show you now the main loop for each cases. As you can see, I have an if statement for each elapsed time, and as you can see, turn variable is the switch turn variable here. And basically, this code is the same in the Weebot and the main controller here. I have like changed it for the camera. I will discuss it later, and what I can need to code the camera for to detect the object and how implemented in the Arduino. Also, if you can see now, the elapsed time is here is the same. 0 to 17 seconds, the first case, and the second phase for the circle, and the other circle also for the third case. And the switch argument is here, case 1 for the motor square, which is driving square, and the case for the rotating left, which is the first circle, and the case for second circle here. And if you can see the Tinkrad, it's basically the same structure of the code. It's the same here for each case, 1, 2, and 3 for each elapsed time. And if you can see, it's drive square in the first one, and then drive circle, and then the reverse circle for different H shape, to make the H shape as demonstrated. And the case of the obstacle avoidance and checking the camera, it's in this case. This part is the demonstration of the parts connecting to the Arduino, like camera and GPS and compass. And as you can see, this is Arducom Mega camera by the company Arducom, and it's a camera as the flowchart here begin. I'll show you the coding for it, and if you see the sketch on how to connect this camera to the Arduino using the own company sketch provided and its own flowchart. How can you read data from this camera Arduino part, including the library for Arducom Mega here, and how can you read the image and also each pixel of the camera, and you can decide, as mentioned, that we bought, and also figure out how we can define the red object, and then after that I can stop. So this is the other one is the GPS MEO60M GPS module. It's give us the longitude and the latitude. Give us unique graphic coordinate for every point on Earth surface. Can use to navigate specific location using GPS technology. And this is the code and also the library provided by the MEO6M. And I can get the latitude and also the longitude, and based on that I can define my current coordinate and also the destination coordinate, and I can go to, and I can know my direction using compass. I'll show you here. As you can see, this is the sketch for GPS module, and also this sketch is for compass, which is IMU module, and each of them have connected to Arduino Uno. Compass declaration for each direction from east, west, and south and north, and getting this data from the compass, I can know my direction, and I can use this direction and calculate the theta dot as designing a differential drive robot using Inventor. And you can see from engineering drawing dimension for the differential drive robot by using a caster wheel and 2 wheels drive by DC motors. I will demonstrate the connection of mounting for each DC motors, and also 3 distance sensor for each. And here, the mounting for distance sensor at the front view of mobile robot is mounted by the screw and nuts for each distance sensor, and each distance sensor is mounted in each direction, left, right, and front, to measure distance for each upper chassis and lower chassis. The lower chassis has a board for connection of Arduino Uni at the end, and the bottom chassis connected 2 DC motors to it, and caster wheel here showing, and at the upper chassis battery, and the other chassis for the force sensor. And you can see the center of gravity is at the center of the robot, so it's very stable. And it's also at the front of the mobile robot board for connection of battery and also force sensor, and it's possible for. This part is for distance sensor, and this is a timer 55 timer, represent as transmitter for LED, and it's been calculated to make frequency as same my student number, 10,000 kilohertz, 0.625, and as you can see from the simulation, it represents my student number. And here, distance sensor As you can see, the AC current represents the photodiode that received the frequency of 10 and 625 hertz, with the 0.04 is the, you can see, the minimum current of 1 meter for a photodiode to generate the current, and a circuit for current to voltage converter here for operation amplifier. As you can see, you can get a conversion from current to voltage and amplify this voltage by 10, so you'll get 10 times the voltage from this channel, as you see, and then pass it to a band pass filter of 10.6 kilohertz, represent my student ID, and pass it to a rectifier circuit with 2-diode precision rectifier to get rectification for the amplitude for the negative part, and finally pass it to low band filter as here to get a DC current, but the DC current here signal is very low, so it's need to be amplified by 10, so pass it to another 10 amplifier, non-inverting amplifier. So I can, as you can see, channel A is like 13.2 millivolt and the output is 183 millivolt. So if the distance get closer, for example, the photodiode will generate 300 microampere, and with the offset, for example, 10 microampere, the offset will be filtered, and if you can see here, you can see the maximum signal will be 5 volt, which is the full range of the Arduino can have for analog to digital conversion, and here demonstrated as a signal of distance sensor. So if it's more than 1 meter, you'll get 103 millivolt, and if it's like very close, it will be 5 volt.